This is section 9.5 of Rosen, Discrete Mathematics and its Applications. We are discussing a type of relation called an equivalence relation. Oh, sorry, there's the summary. We'll talk about relations, equivalence classes, and then a type of equivalence called, well, the relationship to partitions. Equivalence classes, it turns out, are the same as partitions. We'll define that later. What is an equivalence relation? Well, this is a relation on a set A or from A to A, and it is said to be an equivalence relation if it is reflexive, symmetric, and transitive. So those will be the things we test for when evaluating whether something is an equivalence relation. And then if two elements, A and B, are related by an equivalence relation, we call those two elements equivalent. Sometimes we'll use this symbology of A with a squiggle and B to say that they are equivalent with respect to that equivalence relation. Okay, let's use an example. In the set of strings, we could set up a relation R that A is related to B if and only if the length of string A is equal to the length of string B, where L at X is the function that provides the length of the input string X. Is it an equivalence relation? Let's check each of the required properties. First, let's look at reflexivity. Because the length of A is equal to the length of A, then A does relate to A, so it is reflexive. For checking symmetry, we suppose that A relates to B. That means the length of A equals length of B. But of course, equality can be stated either direction. Length of B equals length of A, and therefore B relates to A. So it is symmetric. How about transitive? To set up transitivity analysis, we assume A relates to B, B relates to C. That means length of A is equal to length of B is equal to length of C, and therefore length of A equals length of C, which means that A does relate to C. So yes, it meets all three properties. So the relation ARB, where the length of the two strings is the same, is an equivalence relation. Let's look at another example, congruence modulo M. All right, I'll state what the relation is. We've got M is an integer that's strictly greater than 1. Then the pair AB is going to be in the relation when A is congruent to B modulo M. All right. First of all, just mention that the definition of congruence modulo M is detailed in chapter 4.1, but I do provide it here. So A is congruent to B modulo M if and only if M divides the difference A minus B. So that'll be how we check to see if something is congruent modulo M. Question is it an equivalence relation? Let's check reflexivity. Well, A is congruent to A mod M since A minus A is 0, and 0 is divisible by any non-zero number. We can write it as 0 is equal to 0 times M. So yes, it is reflexive. How about symmetric? Well, suppose A is congruent to B mod M, then A divided by B is divisible by M. That means we can write A minus B as an integer times M. And once I do that, I can multiply both sides by a -1 to get B minus A is equal to negative K times M. But negative K is just an integer, so it means that B minus A is also divisible by M, and therefore B is congruent to A mod M. All right, so symmetry is present. Let's check transitivity. We'll suppose that A is congruent to B mod M, B is congruent to C mod M. That means M divides A minus B, and B minus C, which means we can write them as equations with integers K and L, such that A minus B is equal to K times M, B minus C is equal to L times M. If we add these equations together, we get A minus C on the left, and we get K plus L times M on the right. That means M times an integer equals A minus C. That means M divides A minus C, and so A is congruent to C mod M. Meets the third requirement of transitivity, so yes, a congruent modulo M is an equivalence relation. Let's look at a counterexample. This is the divides relation. We'll show that it's not an equivalence relation. What is the divides relation? The divides relation is A divides B if B is equal to some integer times A. In other words, if B is a multiple of A. All right, we got to check for reflexivity and symmetry, but we'll see that it's not, reflexivity and transitivity rather, but we'll see that it is not symmetric. Reflexivity. Yes, A does divide A for all A. We're dealing with positive integers here, so we're not talking about 0 would not be allowed in that case. Transitivity. If A divides B and B divides C, then we see that B is a multiple of A and C is a multiple of B. If I substitute AK in for B right there, I'll see that C is a multiple of A. That means A divides C. That means the relation is transitive. But we have one more to check, and that is symmetric, and we see that it is not symmetric. All we got to do is find a counterexample. 2 divides 4, but 4 does not divide 2. 2 and 4 is in the relation, but 4 and 2 is not. So it is not symmetric, and therefore not an equivalence relation. All right, that's some examples and counterexamples of equivalence relations.